So let's talk about first order reactions. We can depict a first order reaction. Let's just say we have a decomposition reaction, one reactant, and we can have one or more products over here. But there are lots of first order reactions. And so it might be useful to determine what we call an integrated rate law. So first of all, we're going to go ahead and express the rate law for a first order reaction, a very simple form. So that would be rate is equal to K times the reactant A, and it's first order. We don't have to put the 1 up there because we understand that if there is no exponent, that it is first order. Now, as you've seen, we can actually express the rate of disappearance of A as negative change in the concentration of A with respect to the change in time, and that would just equal K times A. Now, this is the expression of what we would call the average rate of disappearance of A, or the average rate, okay? And what we want to do is we want to come up with an expression that describes the instantaneous rate. And if you remember, the instantaneous rate is going to be a tangent to the curve, which is essentially the derivative at some point on the curve for that reactant. And so we can express this as minus d of A. We're just taking the derivative dt. Okay, and that is going to equal K times A. We need to get all of our terms on the same side, so I'm simply going to divide both sides by A, multiply both sides by minus dt. I'm just going to move the minus sign over there. And so that's going to give us dA over A is equal to minus K dt. I've got my change in time over here on the right-hand side and the change in concentration over here on the left-hand side. Now that we've got our differential equation, we can go ahead and we can integrate the reaction. K is a constant, so we can pull it out of the integral. Here are the boundaries of our integration. We've got A at times 0, that's our initial concentration, and that's going to be equivalent to time 0, and then A at some time t, which will be equivalent to, we'll just call it t. So we've got A, our starting concentration, A naught, and then we've got A at any time t, and over here we have time 0, and then it's some times t. And so when we integrate this, we come out with the natural log of A at times t minus the natural log of A initial, and that's going to be equal to minus K, and we're simply evaluating the time, so this is going to be sometime t minus the time at 0. And so all that really gives us, if we continue with that, is a natural log of A at times t minus the natural log of A at times 0 minus kt. Now let's just do a simple rearrangement of this equation and come up with natural log of A at sometimes t is equal to minus kt plus the natural log of the starting concentration. I just added the natural log of A naught to both sides. And the reason that I did that is to come up with the equation of a straight line. So this is m, this is x plus b. And you might remember this from algebra. That's just the equation of a straight line. On the y-axis, we have the natural log of a at sometimes t. The slope is simply going to be minus k. And then x is time, that's on the x-axis, and then we have the y-intercept, b, which is going to be the natural log of a on the at the beginning of the reaction. So if I draw a very crude graph here, we have time, that's our x-axis. Our y-axis is going to be the natural log of a at sometimes t, and this is going to be a terrible straight line because I'm just no good at free-handing this on this graphics pad. You'll have the slope of the line, which will equal minus k, so that's your slope, which is the minus of the rate constant k, and all you have to do is take the positive of that, and you can get the rate constant. Okay, and then over here you've got the y-intercept, which is going to be the natural log of the starting concentration. So this is an extremely handy thing to have. We call this the first order integrated rate law. That's what this is, the first order integrated rate law. And you're going to want to know that, or at least know how to use it. Okay, so let's move on. So first order reactions, as I said, there are lots of them. Here is the rate law for a first order reaction. We integrate it as I just described, which gives us the equation for a straight line, y equals mx plus b, where the rate negative of the rate constant, that's the slope of the line. You know how to determine the slope. And if you simply do that plot and time on the x-axis, you can determine, number one, whether a reaction is first order or second order or zero order. And you can use it to solve problems for different concentrations or different times, or for the rate constant. So it's a very useful device. So let's take a quick look at how we might use it. If this is the raw data that you develop for a reaction, here's time. We're going to put that on the x-axis. Here's the pressure, and it's in torr, which is just fine for this, at a particular temperature. We can graph that and we get a curve. Now, there's no way from looking at this curve to tell whether this is a first order reaction, a second order, a third order reaction. But if instead of graphing the pressure, which it can be used as a unit of concentration for a gas phase reaction, if I graph the natural log of the pressure versus time, and I wind up with a straight line, I automatically know that this is going to be a first order reaction. Okay, and if it's a first order reaction, I can calculate the slope of the line, which is going to give me the negative of the rate constant. That will give me the rate constant. I know that we've got the y-intercept up here, which is the natural log of the starting concentration, so I can determine that starting concentration if I didn't already have it, and I can determine what the concentration is at any particular moment in time along this particular curve. So, clicker question. For a first order reaction, the plot of the natural log of the concentration of a reactant A versus time can be characterized as, hopefully you understand, this is a straight line with the negative slope, or with a negative slope. Let's do a quick example of this. Based on the previous graph, determine the first order rate constant and the half-life for the reaction. Well, half-life's going to take a little bit more information, but let's go ahead and determine the rate constant. based on the first order integrated rate law, and we'll give you a little bit more information to get the half-life later. All right. So graph. Here's our graph of this first order reaction, natural log of pressure versus time. And all we're going to do is we're going to pick two particular points, a natural log graph versus time, and we're going to calculate the slope of this. Now remember, this is the natural log of concentration versus time, which is just m, okay? And we know that that's going to be equal to the negative of k. So here is time 0. This is the x value, and this is x sub 1. This is the y value, y sub 1. Over here we have x sub 2 and y sub 2. And we're simply calculating the slope of the line. And you know how this works. The slope of the line will be the change in y, okay, with respect to the change in x. So it's just going to be x sub 2 minus x sub 1 in the denominator, y sub 2 minus y sub 1 in the numerator. And so that's going to be 3.11 minus 6.22 divided by 15,000 minus 0. And so that is going to give us minus 3.11 divided by 15,000. So that gives me minus 2.07 times 10 to the minus 4. Now that's the slope. It's not the rate constant. The rate constant will be the positive of the slope. And so our rate constant, k, will equal 2.07 times 10 to the minus 4. And since this is a first order reaction and our time is in seconds, we'll have 1 over seconds, or seconds to the minus 1. These two, 1 over seconds, is equivalent to this. These two represent exactly the same value, okay?